Hello, and welcome to CodeQL as an auditing oracle. In this talk, me, Bas Alberts, and my coworker, Augustin Gianni, are going to take you on a tour of CodeQL and how we use it for code auditing. We're going to be using two components. We're going to be using the CodeQL command line to create databases, and then we're going to be using the Visual Code extension to interact with those databases from an IDE environment. So getting that bootstrapped is pretty straightforward. I have a little convenience script that I use that'll set up the CodeQL command line, and then we'll manually set up the Visual Code extension. So we'll run our little bootstrap script. And all that does is fetch the command line binary release and then clone the QL repo as a sibling of where it places the command line. And then we will also install the CodeQL extension from the extension marketplace in VS Code. And then as a last step, we're going to set up the VS Code starter workspace. So now that we have a working CodeQL environment, let's talk a little bit about what CodeQL actually is and does. So the core idea behind CodeQL is that it will lift the abstract syntax tree of a program and represent that into a relational database. And then we can use the QL language to query that database. And QL is a declarative logic query language. So we say what we want, not how we want it, and QL figures out how to get that for us from the database. And we can ask logic-based questions about code. So essentially it turns code into data, but not in the Lisp sense of the term. So having this gives you a powerful primitive to reason about code. It has object-oriented features that make working in the language pretty straightforward, as opposed to something like a direct data log implementation. And the CodeQL tooling basically has extractors for all the supported languages, and those extractors are responsible for taking the AST of the program and representing that in the database. And then in the database, it's essentially a regular relational database. It's just tuples of values, ordered values. Okay, let's take you on a quick tour of QL and get you bootstrapped into the language so that the rest of the talk actually makes sense. To do that, we'll poke at one of our little test databases. I made a slightly more secure, but only slightly so, version of the demo.c, and we'll lift that into a CodeQL database as well. So that database gives us a representation of the AST of the program, and that lets us query the database about things that are present in the program. So all the statements, expressions, conditionals, basically everything that makes up the program is encoded into that database. And we can query that. And then QL has logic built on top of that and types defined on top of that. So it'll have a sense of the control flow graph of the program as well as the data flow graph of the program. And we can ask interesting questions about that. So as an example, here we have a query that will essentially just list all the function calls in the program. So QL is a declarative logic query language, like we said. So what's happening here? We're saying import CPP. Basically, the import statement pulls in QL library files and lets you pull in logic that's defined in other files. And in this case, we're pulling in the C++ language support because we're working with a C++ database. And then we're saying from all the things that are function calls, where anything, this is just a true statement, select all those function calls, right? Now, you'll note that I'm speaking in terms of plurals, and that's because really when we're working with QL, we're working with value sets. The database has sets of tuples in it, right? And it's just a collection of sets of tuples that represent data. So when we're making these queries, really what we're doing is constraining these value sets into the things that are the answers to what we care about. All right. So for example, if I run this query, and we get as the results all the things that are function calls in the program, right? So here we see the malloc, and here we see the memcopy, and here we see the super secure. But say we wanted to just have calls to malloc represented, right? So we can do things like where fc get target has name malloc. And then we just get the call to malloc. So this is a very simple example of us constraining our result set. And this idea of constraining a result set is really what you're doing over and over again in QL. You're whittling down all the things that are the program to the things that you care about. And then you can use the various representations that QL presents for the program to get really interesting answers to your questions. Now, there's a couple of concepts that you want to be familiar with. So you have the main structure of the query that we talked about already. And then also the idea of predicates. Now from logic, a predicate is a function that operates on parameters whose body is a formula that's either true or false. And then here, previously we saw that any was a predicate, and in this case, the any predicate in this form always returns true. So what if we wanted to represent this logic as a separate predicate, which we can do. So you can define predicates in CodeQL using the predicate keyword and say malloc is malloc, right? And then we can have it range over function calls. And we can say it's true if fc get target as name malloc. So this is basically a representation of what we're asking here in chunked out into its own predicate. So we can go where is malloc fc, and we would expect to get their same results, which we do. So knowing how to use predicates and how to define your own predicates lets you chunk up your logic, and you can then do interesting things with that predicate. So you can actually run this predicate on its own, because really what we're saying is, for the value set represented by function call fc, which is all the things that are function calls in the program, what are the values that satisfy the formula of its body? And the formula of its body in this case is checking whether or not the function call has the name malloc. So for any value that this is true, that will be the result set of this predicate. So we don't even have to run this as an explicit query. We can just run the predicate itself. And we can do that through something called quick evaluation. So if we do the quick evaluation of the predicate, then we get, again, the same result set, right? So predicates can also return quote-unquote values in QL. And the way that works is you just specify the type of the return value, and then really the return value is treated as just another parameter. It's going to be part of the tuple that satisfies the predicate body. So now that we've worked through some of the basics of QL, let's dive into its type system. And this is really where you're going to be spending a significant amount of your time when working with QL. So like we said, the CodeQL database contains a flattened representation of the abstract syntax tree for the program. Things like branch relations are encoded through the DB scheme. And in CodeQL generally, it's not true for all languages, but for most, derives the runtime representation of the AST, the data flow graph, and the control flow graph at QL runtime from this flattened AST representation that lives in the database. So all the expression statements and conditions, these sets of values that make up the program in the database are represented by, at the higher level, by CodeQL types, either at the database level through entity types or at the QL library level through new types. So types break down into two main groups. You have your base types, which include the built-in primitive types like int, float, string, boolean, and date. And then you have your entity types, which are essentially unary extensional predicates, predicates that describe a set of values, and they map to a set of ordered tuples in the database. They're denoted by the @ sign, and that generally means that they are defined in the database scheme. And that's where you can find their definition. And then you have your new types, which just means that those are types defined in QL itself. And then, QL types, essentially new types, are defined through classes. And this is really where the object-oriented features of the language come into play. Classes can extend existing classes, so they're subclassing, which is essentially generally implication. Means that if B extends A, then B is in A. And then you have concrete classes that represent the intersection of their characteristic predicate and the characteristic predicates of their base types. Where a characteristic predicate is basically a predicate that is the defining predicate for the type that a class defines. And then abstract classes represent the union of all their subclasses, which is convenient when you have an interface that you want to implement in a variety of different ways. Then all the various implementations can be grouped into a single set of values through the abstract class. And classes can define and override member predicates, so there's a notion of virtual dispatch. And then remember, whenever things feel complicated, it all kind of boils down back to, a class defines a type, and a type represents a set of values. And you're always working with value sets when you're working with QL. So as an example, let's dive into the QL type system a little deeper. So anytime you see a type in QL, you can generally right-click it and jump to its definition. And then here we see that the function called type is defined in a class function call, and that class extends the type call and something called @funBindExpression, and that's one of those entity types that we were talking about. So if we look at the definition of the entity type, we actually end up in the database scheme itself, and we see that that's a union of a bunch of other entity types. Here we see the what's referred to as the characteristic predicate, and that's the predicate that is named in the same way as the class, and that specifies what determines whether or not something is of the type that's defined in this class, right? So here it says, hey, this is the domain for this class. From all of these things that are represented by these two types, there's things that aren't necessarily function calls. So the function call type extends these types to say, constrain that down to the things that are only explicitly function calls. And that's, again, called the characteristic predicate. Now, understanding this class system and the way QL types are defined is very useful, because it means that you get to define your own types. So say we wanted our own function call type that only applies to malloc calls, right? So we could do something like this. Class malloc calls extends function call, and then we give it a characteristic predicate that says, let's make it malloc call this get target has name malloc. We could do something like this, right? So now we have basically constrained all the function calls down to just calls that have the name malloc through this characteristic predicate. So this is, an object-oriented way of doing the things that we were doing with our standalone predicates. And then we can just use that as any other type in QL, and we can say malloc from malloc call MC select MC, right? And we would expect to get back just malloc calls, which we do. Let's take what we've learned so far and ask our first useful question. Let's say we want to know which malloc calls take a size argument that is the direct result of integer arithmetic, like an addition or a multiplication. And that might be something we want to figure out to check up on integer overflows that affect allocation sizes, right? A common scenario when you're auditing C code. So in terms of QL land, really what we're saying is like, we have the set of all the malloc calls for all the arguments, for all the size arguments to those malloc calls, which ones of those are also arithmetic operation expressions, right? So that translates pretty directly. Let's just say, and this get argument 0 instance of binary arithmetic operation. So that'll expand the characteristic predicate of the malloc call type that we defined to also check that the malloc call in question has a size argument that is an instance of the binary arithmetic operation type. An instance of really just checks the correct characteristic predicate of this type. So if we check the definition of binary arithmetic operation, you see that it is a abstract class. And then if you recall, when we talked about abstract classes, they really represent all the subclasses that implement that abstract class. So here, for example, we see an add expression extending a binary arithmetic operation, implementing this abstract class. And then here we see a sub expression extending binary arithmetic operation, and so on and so forth. So the binary arithmetic operation really represents all these subclasses that implement it in terms of the value sets, right? And then again, those value sets translate to their actual values as they're represented in the database. So that's a mouthful, but really what we're saying here is, hey, give me a list of all the malloc calls whose size argument is the result of a binary arithmetic operation. So when we run that, we get that malloc back, and that is indeed a malloc that has an argument that is an add expression. So that was your introduction to CodeQL. Let's move on to some actual auditing work.
So in this bit of the presentation, we are going to show you how we take advantage of CodeQL to convert it into an auditing oracle, and hopefully we will convince you of maybe trying to do the same and help you with your job. So the more experience an auditor has, the more they realize that history keeps repeating itself. The same old patterns that lead to vulnerabilities in the past, they keep showing up everywhere, and usually having to come up with novel ideas is the last resort for when you haven't found anything trivial in your target. And even if you do find something original, once you have embraced it, it quickly becomes part of the auditing body of knowledge. So this auditing process is a very repetitive one, if you think about it in an abstract way. So you start locating what you can control, then you proceed to see where your data goes, and then you start pondering about how to put the program in a state which wasn't designed for, which is usually a vulnerability. As it is usually when there is a repetition, there is the opportunity for automation. So certainly it seems useful, at least for me, to have a method to encode all this knowledge in a way that allows us to work faster and more accurately. So this is where CodeQL enters the game for some of the people at the GHSL, the GitHub Security Lab, and also outside of it. So there are a lot of researchers that are using CodeQL as a helper tool for their job. So this is they use it as an auditing oracle that answers the security research questions that the researchers have. So it can be thought as some sort of theorem prover, where the theorems are the bugs and the proofs are the results of a query. As we mentioned before, CodeQL turns the compilation of a code base into a regular database that can be consulted. So having something you can ask questions and get answers is a very potent tool in the toolbox of an auditor, as I will try to convince you as this presentation progresses. So what are some common questions that we can ask the Oracle? If we follow the usual auditing procedure, we start asking for the places that handle user input. So this is basically the attack surface, because if you don't have any way to influence the behavior of the software, there is little you can do in order to attack it. Then we start to get more specific, and we ask more specific questions, such as, can we control allocations, for example? What about controlling the size of memory copies, and etc. So CodeQL has a standard library with lots of queries that model bug patterns in code that are readily available for you to use. We will give you a look into this, and we will try to show how useful they are. So we can use this as an auditing guide to locate the parts of the code base that contain patterns that are likely to become bugs. So the quality of the results that you are going to get are going to depend on the questions that you ask and how they get asked. For instance, if you build a query that it is too vague, you are going to get an overwhelmingly amount of results, and checking those for interesting things will be very time consuming. Alternatively, if you make your query too narrow, you may not get any results, which is equally as useless. And also another thing that is very important is how you ask the questions. So colloquial language does not always translate correctly and directly into logic statements. So care must be put into making sure that we are translating our thoughts correctly into QL. So enough with the silly introductions, let's jump into some practical examples. So each language and framework has its own peculiarities from an auditing point of view. For example, languages such as C and C++ usually have memory safety issues, whereas safer languages tend to have more logical bugs. With this in mind, we can imagine that the questions that we are going to ask the Oracle are going to be different depending on our target. As time passes, the amount of knowledge about an ever-changing code base can easily get too big for a single person to remember accurately. Fortunately, the developers of CodeQL, along with the community, have developed a set of QL libraries that model a fair amount of frameworks and languages for us. In this example, we will explore a project called MailTrain. MailTrain is a Node project that uses Express.js as its backend web application framework. Fortunately for us, the QL standard library has a library that models most of the interesting things in the framework, as we will see in a couple minutes. The database that we use for this can be downloaded from LGTM for your convenience in that URL that you're seeing on the screen. So first thing first, let's explore what's inside express.qll to get a sense of what QL gets us for free. So a QLL file is a QL library which contains a set of types, classes, and predicates that are useful for a particular code. This QL library implements these classes that will help us audit applications that use express.js. So we are going to go to express.qll in Visual Studio Code, and we are going to quickly take a look at it. So I have the file already open. We can see that we are declaring a module and that we have several different predicates that are exported that are not private. So for example, this one, which is called app creation, is going to match the creation of an Express application. So one quick trick is that if you don't know what the body of something is doing, you don't really need to, because if you can interpret the results of the predicate, you don't really need to know the details. So if we quick evaluate the predicate, we can get a pretty clear look, an idea of what the predicate is doing. So in this case, we are going to get a single result, which is going to be the creation of the Express application inside the app.js file. So we saw that we can quickly find the main file of the application, which is usually a good thing. And now we are going to explore the route setup class, which is a particularly interesting part of the code. We are going to see that it is being defined here, and the comment says that it is a call to an express router method that sets up a route. So what it's going to give us is the name of the route and the handler, which are the things that we are most interested in. So in order to use it, we have created a small QL query, which is here, which is importing the JavaScript standard library, and it's creating a setup binding, and it is selecting the setup expression, and it is calling this method, which is going to give us a string with the path to the route. If we run it, we are going to check the details. As we can see, we have the setup part of the code, and then we have the route. This is basically the route. This is a route to the users list, and we can see that we have a lot of information, a lot of places that we can audit. For example, this one, we can take a look. We can see that we get the whole expression selected, and we have here the route and the handler for the route. This is very useful for us, but what happens if we are in a code base that is not known to us, and we want to quickly locate the entry points to the application, and where are the security sensitive areas? So to find the entry points, we are going to use the already modeled sources and sinks from the data flow libraries. So what is a source? A source is an attacker-controlled origin of data. That is, something that produces data that an attacker can influence. For example, an API that reads packets from the network is a source. There are generic sources, such as the standard functions like receive or read, and there are also application-specific ones. As mentioned before, CodeQL standard library has modeled a fair amount of these sources, and these are readily available for you to use. So let's see an example of how to get all the data sources in MailTrain without knowing anything particular about the app. In this case, we are going to use the class called remote_flow_source. And we are going to go to the definition, and we can see that it is an abstract class and it is empty. So how this is getting us any results? It can be a little bit tricky, but because of the way QL language is implemented, any class that implements this particular class is going to give you results. That means that if we use it, we are going to get all the other implementations for free automatically. So if we run it, we can see that we can investigate all the sources in the application. In this case, for example, this is a request, and this is the body of the request. For example, this is the params that are user controlled, and we can see that there is a huge list of things that we can investigate. So now that we have a clear understanding of what is a source, we are going to see what a sink is. So a sink is a place that, if it receives user-controlled data, could lead to a security issue. For example, opening a file can be a trivial operation, but if an attacker controls the path to the file in some way, it could lead to a file disclosure vulnerability. In the same fashion as sources, the standard library has modeled a good amount of sinks, but the way to get them is slightly different from the previous example, in which we got everything automatically resolved. So let's see an example of how to get all the data sinks in MailTrain. Let's go back to Visual Studio Code and open the example. So essentially what we are doing here is creating a data flow configuration and query for any node that satisfies the isSync predicate. As I said before, because of the way this library is developed, we need to first import some libraries that have implemented specific data flow configurations for different types of sinks. In this case, I have imported 4 of them as an example, but there are many more that you can explore. For example, we can go and check this one, and we can see that we have different implementations for all the things that are abstract in the original class. So if we run it, we are going to get all the places in which we have a particular sink. In this case, we have the dollar operator. We have again the dollar operator, but you get the idea. This is a nice way to get to know all the places in which something security relevant can happen. So, in this case study, we are going to explore the Linux kernel by using CodeQL as an auditing oracle, as we have done before. And we will use it to help us navigate the large amount of code that there is in the Linux kernel. So we're going to try to use it to be efficient at it. So in this case, we are going to create a very small configuration because we want the queries to run relatively fast for this presentation, but QL is able to handle a full compilation of the full config pretty comfortably. The full config is basically all the modules and the things that are present in the kernel are turned on, which generates a huge database. So here you can see that the commands used to create and build the database do not differ from the standard way to compile the kernel. The only difference that you may see is that the make command itself is run now by CodeQL. So once this step is finished, you will get a CodeQL database named linux.db that you can load in Visual Studio Code. So let's explore the attack surface. Unless you already know your target, the first question that we have in our minds as researchers is almost always, what is my attack surface? That is, what can we control from the attacker's perspective? In the other examples in this presentation, we have seen that QL models some attack surface for different languages and frameworks, but of course, it cannot model every single project out there. In the case of the Linux kernel, there is nothing modeled, which means that we have to do that ourselves. But do not worry, because as we will see, it is easier than it sounds. So one of the first things that come to my head when thinking about user control input for a kernel is user registers. These registers are basically the saved CPU state when there is a transition into the kernel, and are by definition controlled by the user. In the Linux kernel, the CPU registers can be accessed through the ptreg structure. This means that we are going to need to model an access to a field belonging to that structure. QL has a class that is generic, which is called field access, that models these kinds of accesses to types. So what we need to do is to simply extend the class field access to only match accesses to the type ptreg. So let's check the example and investigate the results. In this example, you can see that we have a class that we have named user registered access, which simply extends the field access type. The expression in the constructor is pretty simple, but if you don't know the terminology, it can be a little bit not intuitive. So each field access is going to get a qualifier, which is this part of the field access. So basically the variable that originated the field access. So in order to get it, you use this predicate, which is going to get you this. Once you get that part, you are going to need to get the type. And this is going to be a little bit involved, because the type of the expression can be a pointer. So in order for us to match it by name, we have to first strip the pointer type. So once we have done this with the strip type, we can match it by name, as it can be seen here. So now we can run the query and see which results we are going to get. So in this case, we are working on the small database. So that's basically the reason why we are getting less than 500 results. So we can explore some of them. So for example, this result, the number 42, is accessing the ESP or the stack register. We can see that it is related with some kind of perf module or whatever, and it is accessing this user pointer, which may be interesting. You can see here that it is also accessing the IP or instruction pointer, and so on and so forth. So now we have modeled the attack surface, one of them. So once you have located the inputs to your target, the next auditing question that we need to answer is, where does all that data that we can control ends up? So this is basically a textbook example of the data flow problem with some special rules. Basically, any expression in the application that deals with user data, even if it is partially controlled by the user, will propagate its taint status forward. The taint status means that the value of something, of any expression or variable, is at least in some capacity influenced by the user input. The concept is similar to data flow, and it is related to it. But the key difference is that data flow propagation deals with exact and perfect copies of data. Implementing this kind of analysis sounds very complicated, and it can be. But fortunately, QL makes it really easy to solve this problem by using the taint tracking data flow libraries. So implementing a taint tracking configuration is as simple as implementing the missing abstract methods in the taint tracking configuration class. There are two main methods that you need to implement. The first one is called isSource. It defines what expression will be considered the origin of the tainted information. In our case, the source is any expression that satisfies the new type that we have created, called user register access. The second predicate that you need to implement is called isSync, which is going to define what expression will be considered relevant if taint data reaches it. In our case, we will create different things that will illustrate security relevant properties of the code base. So we are going to see an example now of how we can do that. So in this example, we have imported the taint tracking module. We have the user register access that we have implemented before, and we have added a configuration that extends this class. And as I mentioned, we have to implement two methods, the isSource and isSync. In this case, we are making the source data flow node. We are converting it to an expression, and then we are checking the type of that expression. If it matches the user register access, then we are going to consider the expression as tainted. In the case of the isSync predicate, we are going to say that anything can be a sync. This is going to allow us to get all the places that are dealing with some tainted data. I usually do this in order to give a first look into a code base. But in the following slides, we are going to see how to make this more accurate. So let's run this example and see which are the results that we get. We are going to get a lot of them, and some of them are not going to be security relevant, but this is just an example for you to get an idea. So now we have some results. For example, we have this result, which is inside the ptrace.h. We see that there is a taint result here. It is using the SP register, and it is moving it to the other variable. So we can see that then this other variable, which contains the initially tainted value, is going to be used in this function. And then we can proceed with the following result, which is the function call that we have here. And here we see that there is no use for this particular tainted value, but we can also appreciate that the taint analysis is performed across function calls, which is a very important thing. So now we have modeled the data flow of the tainted data. We basically know all the places that deal with tainted data, but the results, as I said before, are too many and most of them have no security impact. What we need to do is to make our questions to the Oracle a little bit more specific. We will do this by narrowing the sink predicate. A sink is a place in the code where something security relevant may happen if tainted data reaches it. One example of that is when we can influence the result of arithmetic operations. This of course depends on what the application does with the operations, but we will see later that we can further improve this predicate. In this case, we can see that we have overridden the isSync predicate, and we are checking for the expression to be an instance of a binary arithmetic operation. Let's see the example query and see some results. So we have basically the same query as before, but we have added this small piece of QL. We are going to run it and see the results. So again, we have a bunch of results and we can check them. Here we have the CS register, which is involved in this arithmetic operation that we can see here. And then it goes inside this function, and then again it takes part of another arithmetic operation, and so on and so on. In the same vein as the previous example, if we can influence the index to an array expression, there is a chance that we can access memory we should not be able to access. In this case, the isSync is going to be pretty similar, but we are going to get all the array access expressions, and we are going to match our sync to the array offset. We can see this more clearly in an example. Again, the only thing that we change is the isSync predicate, and we are going to run it. In this case, there are not that many results, but we can check them nonetheless. So we have an access to the SP, then it gets into this function, there is a binary arithmetic operation, and as we can see, the taint information propagates here to another expression, and it ends up in an array access, which is hidden probably by this macro definition. Let's see if we can get a more clear example. But you get the idea. Like for example, this case. This query says to us that we have some kind of influence in this variable. So it is worth taking a look to get the extent in which we can control it. So a classical and ever-present type of bug in C and C++ code is allocating less memory than we need. If the size argument for a call to a memory allocation primitive can be controlled by an attacker, in certain situations it can lead to buffer overflows. In the following slides, we will see how we can model this situation, and we will write a query that allows us to investigate such situations. Since allocations are a common thing in C and C++, QL has modeled some interfaces that will help you model custom and/or unknown allocators. In order to use them, you need to import the allocation interface, as we can see in the QL example here. This is the interface that you have to import. In this case, we are modeling the interface to kmalloc and kcalloc, which are two of the most used allocation functions in the kernel. These two functions differ in the place where the size argument goes. So in this case, for kmalloc, the size is the first argument, and for kcalloc, size is the second one. By overriding the getSizeArg, we allow the internal QL classes to plug in our class and use it in the standard queries such as allocation expression, as we can see in the example that I will show you next. So now that we have linked our kernel allocation primitive, and QL is aware of them, we can use the class allocation expression to show us where there is an allocation whose size is tainted. We have basically implemented the isSync again, but in this case we are going to get all the allocation expressions, and we are going to get the size expression, and we are going to match it to our sync. So let's go to Visual Studio Code and run this query. In this case, I have to change the database because the minimal database that I have been using now doesn't have any result. But if we change to the slightly bigger one, we are going to get some. So let's run it and wait a little bit. As you can see here, I have implemented more than one allocation function. So we are going to get a good chunk of results. So now we have some results. We can check them. So in this case, we are going to pick one. We see that we have the register VX that is flowing into different places. So if we go here, we can see that we have the control on this kernel allocation.
Okay, to finish up, let's run through some tips and tricks, things that we think are useful for you to know when you're using CodeQL for code auditing. So the first feature we want to highlight is the quick query. So quick query is just a way to pull up a quick scratch pad template query for the context of the database that you're working on. So it goes through the command plat and just pull it up like that. And that's convenient because it prevents you from having to navigate the file system to find the right location to make a query file in the workspace and all that stuff. So for example, we can, go back to that little example that we've been working with in our introduction. And that's basically the quick query functionality. So another UI element that you want to be aware of is the query history. So the query history looks like it's just a log, but it's really an interactive history of all the queries that you've run. And this becomes useful when you've been running a lot of expensive queries, right? You have a large database, you've been doing a lot of data flow and taint flow analysis, and those can be expensive queries, even with all the aggressive caching that CodeQL does. So this allows you to recall result sets from previous queries and interact with those result sets. So you don't have to rerun queries all the time. And this saves you a lot of time when you're auditing, because a lot of your auditing is, revisiting previous results. And then the last thing that we wanted to highlight is it's a newer feature released in October 2020, version 134, I think, which is the AST viewer. So the AST viewer is very convenient because so when you pull up a source file associated with the CodeQL database, the AST viewer lets you explore that source file in terms of the AST as it's represented in the CodeQL database, specifically with all the types that CodeQL uses to represent it. And that's convenient when you're trying to figure out what components you need to use in a query to ask the question about the code that you're looking at. So I tend to mock up little code constructs to run them through the AST viewer just to get a handle on which components I should use to ask my questions in the most efficient way. So as you navigate the source file, you can see that it will actually break down the various components of the AST in terms of CodeQL types. So those are the 3 UI features we wanted to be aware of. Then it's a little use case that we find very convenient sometimes when we're looking at larger code bases, is using CodeQL query suites to generate bug density charts. And that sounds fancier than it is, but it's really we're taking account of all the issues that CodeQL finds. And CodeQL comes in the repos with a set of query suites, and query suites are basically just a collection of queries, and they're conveniently broken up in various categories for you already. So for example, you have the full LGTM for the LGTM.com version of CodeQL. C++ query suite, which is all the queries that LGTM runs against C++ databases, but you also have them broken down in terms of categories. So you have, for example, have a security and quality query suite, which includes all the security queries, but also the code quality queries. And that's the one I like to use for generating bug density charts. So for an example that we're looking at the slide, we're asking CodeQL to use this query suite and then to output all the issues that it finds in the serif format, which is the kind of the SAS standard format, and then output it to the file that you specify. One thing I like to do is run a query suite like this. So for example, if we revisit that Linux kernel database that Augustine was working with, we can run the security and quality query suite and dump that to a CSV format, and then have a little Python script that turns that CSV into a very simple horizontal bar chart, and that gives you a nice little overview of the issue counts. And then if you sort the files, you get a nice little overview of the source tree in terms of where a lot of the quality and candidates for security issues are. And that gives us a little density.csv, and then we can use my little scripts on density.csv, and that'll generate a little chart. And that gives you just a visual handle on what parts of the code might be interesting to look at. And then for smaller projects like this, it's maybe not that useful, but if you look at a large project like, for example, Samba, having that kind of visualization lets you hone in on areas of the code that you might actually want to take a closer look at. So I would definitely be interested in taking a closer poke at what's going on over here in this area of the source tree. For learning QL, if you want to go deeper into the language, the QL handbook is good for that. That'll actually break down a lot of the features that we have to skip due to time, such as how do quantifiers work, how does recursion work in QL, and that kind of stuff. The Learn QL documentation is also very useful. It has a bunch of tutorials to get you started. We have a full workshop that Augustine put together for OffensiveCon that has a lot of useful material and exercises. We also have various workshops available. An example of that is the one that we put out for GitHub Satellite this year, which focuses on Java vulnerabilities and audits. We have learning labs available, like the U-Boot Learning Lab, and there's a bunch of content out there that you can use to get spun up on CodeQL and learn the language deeper. We also, since we use CodeQL quite heavily for our own research, you can find a bunch of case studies for real-world results and vulnerabilities that we found with CodeQL and the research section of the Security Lab website. So thanks for watching. If you have questions or comments, we are available in the chat, I believe. And you can contact either me, Bas, or Augustine at the following email addresses. And thank you so much for your time, and we hope to see you in the future, hopefully in person.